Hi everyone, my name is Peiyu, a PhD student from the University of Western Australia. It's my honor to talk about our recent work recalibrating feature attributions for model interpretation. Nowadays, deep neural networks has shown remarkable performance for many real-world applications. Despite its outstanding performance, the deep models is considered a black box model, making it difficult to extend to high-stakes applications. To provide an understanding of the model prediction, attribution methods provide a way to compute the importance of each input feature's false final prediction. Among different attribution methods, integrated gradients are one of the most popular attribution methods due to its desirable axioms, including completeness and implementation invariance. For example, completeness requires the summation of the attributions to be equal to the output change. Equation 1 formally defines the integrated gradients. However, the reliability of the attributions calculated by IG heavily relies on the reference choice, and it has been observed that IG is sometimes unreliable when the reference is not well defined. To solve this problem, many attribution methods are proposed to redefine the references. However, the calculated attribution maps face frequent variations between positive and negative attributions. To address this issue, these attribution methods rely on taking absolute value to generate a plausible attribution and high performance. However, taking the absolute value reorders the estimated attributions for the pixels, which violate the axioms of the attributions. To address the inconsistency, we develop our methods to recalibrate the attributions of existing methods. Our method offers a new approach to finding a desired reference for attribution methods without the need for manual selection. Given an input feature, we first assume its desired reference in the direction of gradient ascent. Attribution can then be calculated along a nonlinear integration path as in equation 1. However, obtaining the desired reference and corresponding nonlinear integral path can be intractable. To overcome this, we develop a method to identify the interpolation points for the integral estimation. We discover that gradients of the interpolations that reside on the integral path will always have the same sign with the corresponding variation. Equation 2 describes how we integrate gradients of these valid interpolations to estimate the attributions. While we made a progress in identifying valid interpolations, it is still intractable to sample enough points in the input space. Here, we leverage the reference in the existing attribution methods to approach the input space through Monte Carlo estimation, and the different references can be viewed as adopting different sampling strategies. This allows us to recalibrate the attributions of integral-based attribution methods. And in addition to valid interpolations, we also propose an efficient approach to recalibrating attributions with valid references. It is important to note that current attribution methods with invalid interpolation points will lead to subnormal attributions. Taking the expected gradients as an example, the following example illustrates the process of recalibrating the attribution of a single input pixel with valid interpolations. Given an input image, we can first obtain a set of interpolated images. Then we can assume our desired reference between these interpolations. In the second step, we can compute the variations and gradients on these interpolations. Based on our previous insight, we know that the sign of variations and gradients will change when the interpolations cross the input feature and desired reference. Therefore, we can identify valid interpolation points by checking the sign of the product between the variations and the gradients. Finally, we estimate the attributions over the valid interpolations, resulting in recalibrated attribution of the input pixel. To assess the effectiveness of our proposed method, we conducted 3 quantitative experiments. Firstly, we evaluated the accuracy change between pixel insertion and deletion games on 5 popular integral-based attribution methods. Next, we reported the results of the accuracy change on the DeVry benchmark. And finally, we compare our methods with vanilla attributions on sensitivity N. And overall, our method consistently improves the performance of popular attribution methods across all 3 benchmarks, demonstrating the effectiveness of our recalibrating methods. There are some major references of our work. Thank you for listening.